Swayam Prabha. Digital India. Educated India.
Hello students, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasamanda Tukadoji Maharaj, Nagpur University. In this particular course of BSc Semester 1 Inorganic Chemistry, as per the curriculum of BSc Chemistry Honours, we are discussing about atomic structure. Now we have discussed in 3 different lectures about the atomic structure and what are the various models of atomic structure given by various scientists and the ultimate outcome of that. Now in this particular lecture we will be discussing about a few typical questions that may arise in the minds of the students, and also they are there in the examination. So we will go through a few typical questions based on atomic structure topic. Let us go through them one by one. This lecture is prepared under the academic expertise of Professor L.J. Paliwal. Let us start with the first question. Now, can Heisenberg uncertainty principle be applied to stationary microscopic particles? This is a question. So, if you have a particle which is present at one particular position, then can we apply Heisenberg uncertainty principle to it? Now let us see. For stationary particle, we know that the velocity is equal to 0, and so the momentum P, which is equal to mass into velocity, this will become 0. And if the momentum is 0, then position can be determined very accurately. It means that uncertainty in position becomes 0, and hence it is not possible to apply this principle of Heisenberg uncertainty principle to the stationary particles. That's why the statement of the Heisenberg uncertainty principle itself involves the particles in motion. So this principle states that it is impossible to determine the momentum and the exact position of microscopic particle which is in motion simultaneously and accurately. So this particular concept is only for the particles in motion like electrons or photons, which are having mass and which are moving with very high velocities. Coming to another question. If gaseous molecules of ozone and oxygen are moving with same velocities, what is the ratio of their wavelengths? Now this question is based on the concept of de Broglie matter waves. Now we know that according to de Broglie equation, the wavelength of a material particle is related to its mass and velocity as lambda is equal to h upon m into v, or in other words, we can say that this lambda is proportional to mass of the particle if they are moving with the same velocities. Since it is with the same velocities, we can say that if velocity is constant, then and also h is constant, then lambda will be proportional to 1 upon m. That is, lambda is inversely proportional to mass of the moving particle. Now, the atomic masses of ozone the molecular masses of ozone and oxygen are 48 and 32 respectively. So we know that O3 has a molecular mass of 48 and O2 has a molecular mass of 32. Putting these values, we can say that this lambda of oxygen molecule upon lambda of ozone molecule, since it is inversely proportional to their molecular masses, then this will be equal to mass of the ozone molecule upon mass of the oxygen molecule. We can see that there is an inverse relation between the two. And putting these values, we get 48 upon 32. that is equal to 1.5. In other words, we can say that the wavelength associated with the oxygen molecule will be 1.5 times as compared to the wavelength associated with the ozone molecule if they are moving with the same velocities. Let us calculate the wavelength range of Balmer series. Now we know that for Balmer series, the value of N1 is equal to 2 and N2 value will be 3, 4, 5, etc. We know that the Balmer series is obtained when an electron jumps from higher energy levels to second energy level. So this value of N1 is fixed while the value of N2 goes on varying from 3 to infinity. So putting these two values in the equation, nu bar is equal to RH, which is a Rydberg constant, into 1 upon N1 square minus 1 upon N2 square will be equal to 1.528 into 10 raised to power 6 meter inverse. Now this is the wave number. Wavelength is related to wave number as lambda is equal to 1 upon nu bar, and that comes out to be 6545 angstrom. So this is the wavelength of the first Balmer line, which is obtained when an electron jumps from third energy level to second energy level. So this is the first Balmer line. Now the last Balmer line is obtained when the electron jumps from the highest energy level to the second energy level, that is N2 is equal to infinity and N1 will be equal to 2. Putting these two values in this equation, so we have nu bar is equal to Rydberg constant into 1 upon N1 square minus 1 upon N2 square. Here N1 is equal to 2 and N2 here comes out to be infinity because electron is coming from the maximum energy level, or we can put it as an infinity value. So this value becomes 0 and ultimately the value of wave number comes out to be 2.75 into 10 raised to power 6 meter inverse, or the wavelength comes out to be 3636 angstrom. Now if we see these two values carefully, we will find that this value as well as this value belongs to the visible region of the spectrum. Hence we have already said in previous lecture that the Balmer series is the only series in the hydrogen spectrum which is entirely present in the visible region of the spectrum, because if we convert it into nanometers, it will be 654 nanometers to 363 nanometers, and we know that from 350 to 750 nanometers the range belongs to the visible region of the spectrum. Let us calculate the energy of electron in the third Bohr shell of hydrogen atom. So now we have energy in the nth shell of any atom is equal to minus 13.6 Z square upon n square. This Z is the nuclear charge or atomic number, we can say. N is the number of the shell, and the negative sign indicates that the energy is less by this particular factor as compared to the energy of the free electron, because when the electron is free, its energy is assumed to be 0, and when the electron is bound to the nucleus in an atom, there will be definitely net release of energy due to attractive force between the nucleus and the electron. So this is negative sign. For hydrogen atom, Z comes out to be 1, and for third shell N comes out to be 3, and hence the energy of this electron comes out to be 1.511 electron volt. Now 1 electron volt is equal to 1.602 into 10 raised to power minus 19 joule. So converting electron volt into joules, what we get is energy of electron in the third Bohr shell comes out to be 2.42 into 10 raised to power minus 19 joule. So this is how we can calculate energy of electron in any Bohr shell. It can be third shell, fourth shell, fifth shell, and so on. Let us calculate the radius of the fifth Bohr shell in hydrogen atom. Again, now the radius of the nth Bohr shell is given by n square h square upon 4 pi square m e square into z. Again, n corresponds to the number of shell, h is the Planck's constant, pi is constant, m is the mass of electron, e is the charge on electron, and z is the atomic number, which is equal to 1 for hydrogen atom. Putting all these values in this equation for the fifth Bohr shell, n equal to 5, h Planck's constant value we have put, and all these values when you put together, what we get is the radius of the fifth Bohr shell comes out to be 13.26 angstrom, or in other words, it is 13.26 into 10 raised to power minus 10 meters. Which of the following set of quantum numbers are invalid and why? We will try to solve this particular question. If you have given a set of quantum numbers like n, l, m and s, let us see one by one set. So this is the first set consisting of 4 quantum numbers, n equal to 2, l equal to 0, m equal to -1 and s is equal to -1/2. Now we know that the spin quantum number is either +1/2 or -1/2. It can have any value among the two. So let us compare these three. Now for n equal to 2, L will have two values, 0 and 1. Out of that, the value of L given is 0, which corresponds to S subshell. No problem at all. So 2 is correct. This L is equal to 0 is correct. So n equal to 2 has no problem. L equal to 0 has no problem. Coming to M. Now M will have 2L plus 1 values ranging from -L to +L. Now since L equal to 0, -L to +L comes out to be 0. So M can have only one value, that is equal to 0. Whereas here the value of M given is -1. Now this is not a correct quantum number in this particular group. So we can see that this particular set of quantum numbers is incorrect or invalid, because for n equal to 2, L can have value 0, but for L equal to 0, M cannot have value equal to -1. So this is an invalid set of quantum numbers. Coming to the second set. In this set, we have n equal to 1, talking about the K shell. For n equal to 1, L can have only one value, that is equal to 0, that is also correct. M can have values from +L to -L, which is equal to 0, no problem. And S can have value +1/2 and -1/2. So this is again a correct set of quantum numbers. There is no problem in this particular set. Coming to the third set. So now you have n equal to 2. So since n equal to 2, L can have only two values starting from 0. So L will have value 0 and 1. But here the L value is given as 2, which is not possible. So for n equal to 2, L can have only two values, 0 and 1. So this 2 is an incorrect value. Okay. Now if this 2 is incorrect, then M, now this maximum value of L can be 1. M can have any values 0 and 1. And S can have value +½ and -½ So this is an incorrect set of quantum numbers. Coming to the next one. For n equal to 2, we are talking about L shell. L can have values from 0 to n-1, that is equal to 1. So 0 and 1, two values of L are valid. So this is a valid value. But when we come to M, M can have values from +L to -L, that is +1 to -1, whereas the value given is +2, which is incorrect value, and hence this set of quantum numbers is again an invalid set. Coming to the last one, n is equal to 2, we are talking about the L shell, and in L shell, L can have values 0 and 1, so 1 is the correct value. Similarly, M can have values from +L to -L, that is +1 to -1. So -1 value is a valid value, and s is equal to plus 1 by 2 is again a valid value. So this set of quantum numbers is a valid set. So there are 3 invalid sets of quantum numbers and there are 2 valid sets of quantum numbers. Okay, now let us see what is the angular momentum of electron revolving in the p orbital. So if an electron is revolving in a p orbital which is having a dumbbell shape, what is the angular momentum of this electron? Now we know that the angular momentum depends on the azimuthal quantum number, as angular momentum is equal to under root of L into L plus 1 into h upon 2 pi. Sometimes this h upon 2 pi is represented by a symbol h cross. So for an electron in the p orbital, the value of this L comes out to be 1, because we know that for s orbital L equal to 0, for p orbital L equal to 1. So putting this value of L here, what we get is 1 into 1 plus 1 under root of this. So this comes out to be root 2 into h cross or h upon 2 pi. So if we cancel this, what we get is angular momentum is equal to h upon root 2 pi. This is the value of angular momentum. How many nodal planes are present in the following orbitals? Let us calculate the number of nodal planes in various orbitals. For example, for 3px orbital. Now for 3px orbital, we know that the value of principal quantum number is 3, and for p subshell we have azimuthal quantum number is equal to 1. So number of nodal planes are given by n minus L minus 1, which is equal to 3 minus 1 minus 1, which is equal to 1. So 3p orbitals or 3p subshell or any orbital in the 3p subshell like 3px, 3py, 3pz, all of them will have one nodal plane. And if we plot the probability distribution curve, we will find that there is a nodal plane which is having almost 0 probability of finding electron. So electron can be found in this particular region or most probably in this particular region. In between, there is a zone of almost 0 probability or negligible probability, and that is called as a nodal plane. Coming to another orbital, 4f xyz orbital. Now for 4f subshell, we know that n, the principal quantum number, equals to 4 and the azimuthal quantum number L equal to 3. For this particular combination, we have number of nodal planes n minus L minus 1, which is equal to 4 minus 3 minus 1 comes out to be 0. It means that this 4f subshell will have 0 nodal planes. Whatever is the orbital in the 4f subshell will not have any nodal plane, and its probability distribution will be something like this without any nodal plane. Nodal plane is actually the minima between two maximas, as we are observing in this particular case. There is no minima in between two maximas. Coming to the 5py orbital. Now for 5py orbital, we know that for 5p subshell n equal to 5 and L equal to 1, and hence n minus L minus 1, that is equal to number of planes, comes out to be equal to 5 minus 1 equal to 3, and this can be shown as this particular diagram. So 5p subshell can be shown like this with 3 nodal planes, 1, 2 and 3. So there are 3 minimas with almost 0 probability or negligible probability of finding the electron between various maximas. So this is about 5py orbital. So in this manner, we can calculate and we can show the nodal planes in various probability distribution curves. Let us calculate the spin multiplicity of P4 and D4 configurations. These are two examples we are considering. So P4 configuration, like oxygen is having P4 configuration, the D block elements may have a D4 configuration. Let us calculate the spin multiplicity of these configuration. For P4 configuration, the electron distribution according to Hund's rule of maximum multiplicity, as the first electron goes to the first orbital, second orbital, then the third orbital, and then the pairing will take place in the first orbital. Okay, and so for this, the total spin quantum number will be this plus 1 by 2 and minus 1 by 2 will get cancelled. So only 1 by 2 plus 1 by 2. So the total spin quantum number comes out to be plus 1. And the multiplicity is given by 2s plus 1. And this 2s plus 1, if we put s equal to 1 over here, so 2 into 1 plus 1 comes out to be equal to 3. So multiplicity of this state comes out to be 3. Similarly, for d4 configuration, now we know that there are 5 d orbitals which will be filled singly with 4 electrons, and because of this the total spin quantum number will be plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2 comes out to be 2, and so the multiplicity comes out to be 2 into 2 plus 1, which is equal to 5. Hence the multiplicity of d4 configuration is equal to 5. Multiplicity of p4 configuration equal to 3. What is the physical significance of magnetic quantum number? Now we know that magnetic quantum number can have values plus L to minus L. The magnetic quantum number represents the orientation of electron in the presence of external magnetic field. Now when an electron is placed in an external magnetic field, then there are two motions which are taking place. First motion is the spinning motion of the electron, where electron is revolving around its own axis, similar to a top revolving around its own axis. But when it is placed in a magnetic field, then there are possibilities that the electron magnet, or because electron is continuously revolving around its own axis, it is behaving as a bar magnet. And when such a bar magnet is placed in external magnetic field, suppose the external magnetic field is applied along the z-axis, then there are number of possibilities that the electron can align its orientation in the direction of magnetic field or opposite to direction of magnetic field, or it may not get affected at all. For example, if an electron is present in an orbital with L is equal to 0, then in that case there will not be any effect on the motion of the electron or movement of the electron or orbital motion of the electron when the external magnetic field is applied. But if it is placed in an orbital with L is equal to 1, then there are three possibilities. Electron can remain over here, it can align in the direction of magnetic field at a particular angle, having this value of orbital angular momentum is equal to h cross or h upon 2 pi, or second probability, it can oppose the applied magnetic field with minus h cross. Similarly, if the electron is present in an orbital having L equal to 2, then it can align in 5 different ways. In one case there is no effect, in second case there will be plus half, plus h cross, plus twice h cross, minus h cross, minus twice h cross. So these are the possible orientations. So when we say that the magnetic quantum number is 0, meaning that it has no effect of the applied magnetic field. If we say that magnetic quantum number is plus 1, it means that it is aligning in the direction of magnetic field with an orbital angular momentum of h cross. Similarly, if it is plus 2, then it is having an orbital angular momentum of twice h cross, and so on. Let us see what is the main shells in the atom. We represent the main shells or the main energy levels as K, L, M, N, O, P, Q, etc. Now, what is the electron capacity of P shell? We know that for K shell the capacity is only of 2 electrons. For L shell it is 8 electron. For M shell it is 18 electron. What will be the capacity of P shell? We are not talking about the P subshell. Subshell is represented by small letters, whereas the shells are represented by capital letters. So we are talking about the P shell. Now for p shell, it is the sixth shell, and so the principal quantum number n equal to 6. And so the maximum electron capacity is given by 2n square. So that is equal to 2 into 6 square, coming out to be 72. So p shell can have 72 electrons in it. What will be the electronic configuration of iron in +2 and +3 oxidation states? So let us write first the electronic configuration of iron with atomic number 26. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s2. Now, when the electrons are removed in +2 oxidation state, the 4s electrons are lost first, because the fourth shell is the outermost shell. When the electrons are filled, the electrons are filled first in 4s and then in 3d. But when the electrons are removed, they are removed from the outermost shell first. And so, in +2 oxidation state, these 4s electrons are lost, and hence the electronic configuration will be Fe2 positive with 2 less electrons as compared to this. So there will be 24 electrons with 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6. But in case of +3 oxidation state, we know that both the 4s electrons are lost, and still one electron is to be lost, that will go from the next energy orbital, which is the 3d subshell, and hence we have Fe3 plus having the configuration 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5. One more electron is lost from here. Okay, now the velocity of electron in the first Bohr orbit is 2.19 into 10 raised to power 6 meter per second. Let us calculate the radius of this orbit if mass of electron is 9.1 into 10 raised to power minus 31 kg. The angular momentum of an electron in the nth Bohr shell is given by mvr is equal to nh upon 2 pi. Now, the radius can be calculated putting all these values. M is the mass of electron, which is 9.1 into 10 raised to power minus 31 kg. V is velocity, which is given as 2.19 into 10 raised to power 6. R is to be calculated. N is the nth Bohr orbit. We are talking about the first Bohr orbit. So N will be equal to 1. H is 6.626 into 10 raised to power minus 34 divided by 2 into 3.14, and putting all these values, calculated value of R comes out to be 0.0529 into 10 raised to power minus 9 meter, or that is equal to 0.529 angstrom. So that is the radius of first Bohr orbit. Which energy level of Li positive ion has the same energy as that of the fourth energy level of hydrogen atom? Now this is a complicated question. We will see that this is Li2 positive ion. It is having a single electron in it. So we call this as a hydrogen-like atom. And so we can apply the Bohr's theory to this particular atom. And we can calculate its radius or Bohr's radius of that particular electron. Now the question is, which energy level of Li2 positive, means N is to be calculated, and that has the same energy as that of the fourth energy level of H atom. So we are talking about the fourth shell of hydrogen atom. Let us see. Consider that the hydrogen atom or the first energy level of hydrogen atom has an energy equal to E1 of H. That is the first energy level of hydrogen. Its energy is given by E1H. Then the energy of fourth energy level of hydrogen atom will be given by E4H. And this E4H is equal to E1H divided by N square, that is equal to 4 square. This is the relation between the energy of the first shell and the nth shell. Okay. Now, similarly for Li2 positive ion, the energy of the first energy level of Li2 positive will be given by E1 of Li2 positive upon n square. Hence, energies of the first level of hydrogen atom and Li2 positive ion are related as, now we know that we have which energy level of Li2 positive has the same energy as that of fourth energy level of hydrogen atom. So now we have to compare the energy levels of these two, and the comparison is given by first energy level of Li2 positive is equal to first energy level of hydrogen into Z square, and here the Z value is equal to 3 because lithium has nuclear charge or atomic number equal to 3. So we have E1 of Li2 positive is equal to E1 of hydrogen into 3 square, and putting this value in these equations, so we have E1 of hydrogen upon 4 square, that is the first energy level of, or the fourth energy level of hydrogen, is equal to E1 of Li2 positive upon n square. This n is to be calculated, which is equal to, now we can put it as E1 of hydrogen into 3 square upon n square from this equation, and from this now E1 of H and E1 of H of this will get cancelled. So n square will be equal to 3 square into 4 square, and hence n comes out to be 12. It means that the 12th energy level of Li2 positive has the same energy as that of the 4th energy level of hydrogen atom. What will be the mass of photon of sodium light having a wavelength of 589.4 nanometer? Now this is a question based on de Broglie concept of matter waves. We are talking about the energy of light in terms of wavelength, and we want to calculate the mass of the photon associated with this particular wavelength. So according to de Broglie equation, we know that lambda is equal to h upon mv, or m equal to h upon lambda into v. Putting the values, h equal to 6.626 into 10 raised to power minus 34 joule second divided by lambda is equal to, what is given is 589.4 nanometer is 10 raised to minus 9 meter into velocity of light, because it is a light photon, so 3 into 10 raised to 8. Putting these value, the mass of the photon comes out to be 3.74 into 10 raised to power minus 36 kg. So it is extremely small mass associated with a photon. How many waves of an electron will complete in single revolution in the third Bohr orbit? Now we know that in order to have a constructive interference, the circumference of the orbit of an electron should be integral multiple of its wavelength. The number of waves should be an integral value within the circumference of this particular circle. That is, this circumference, that is 2 pi r, should be integral multiple of the lambda value. Putting these values, so number of waves n will be equal to 2 pi r divided by lambda, and we know that according to de Broglie concept or de Broglie equation, this lambda is equal to h upon p or h upon mv. Putting these values together, what we get is 2 pi into mvr upon h, and we know that this mvr for third Bohr orbit should be equal to 3h upon 2 pi, because we know that the mvr values are quantized, or the angular momentum is quantized with value nh upon 2 pi. So for third Bohr orbit, the value of n equal to 3, so it is 3h upon 2 pi. Putting mvr is equal to 3h upon 2 pi in this equation, what we get is cancellation of these 2 pi and hh. So number of waves come out to be equal to 3. So in the third Bohr orbit, there will be 3 waves of the electron. This is all about this particular lecture based on the questions or the typical questions on atomic structure. Thank you very much.